Hi, welcome to this organic chemistry quick video. This is Pericyclics Part 3, Sigmatropics. As a reminder, there are three main types of pericyclic reactions. First video that we did was cycloadditions, the second was electrocyclics, and then now we're on to sigmatropic reactions. And in sigmatropic reactions, there is no net change in sigma or pi bonds. So the number of pi bonds that you make is from the number that you broke, and the number of sigma bonds that you make is from the number of sigma bonds that you broke. So what is a sigmatropic rearrangement? Well, it's a pericyclic reaction where one sigma bond is replaced with another pi bond from another location. Essentially, it looks a lot like the benzene resonance, where you have this idea of these bonds going around in the circle, and also it's very similar to what we were looking at in our previous ones, where you have this idea of the reaction happening in a circle, but instead of having any change in the number of pi or sigma bonds, you're just rearranging them, which is why it's called a sigmatropic rearrangement. Let's look at a little bit more information about the notation that you used. When you see sigmatropic rearrangements, typically you're going to be hearing this idea of broken and formed. Looking at that first reaction that we just had on the previous slide at the top here, on the left-hand side is our broken, and on the right-hand side is our formed. So on the top, it's the sigma bond is, you have three going across. Let's see, how do I say that? So it is 3 carbons until you get from the broken to the formed, and it's the same on the other side. Okay, so the top is showing you how, let's see, the direction of the electrons going that way. So it's from carbon 1, carbon 2, carbon 3, and that's where you get to your sigma bond that's being formed. And then on the bottom side, it's again 3 until you get to the one that was formed. Okay, from the one formed to the one broken, then from the one broken back to the one formed. If you're looking at the next one, that's showing a 1,5 sigmatropic rearrangement. And so the bond that is breaking and making is happening on that hydrogen, so that's just one atom, saying it right. And then on the other side, there are 5 atoms, so it's a 1,5 sigmatropic rearrangement. Similar idea for a 3,5, that would mean that you have 3 carbons in between where your double bonds making and breaking, and then 5 on the bottom. And that's kind of how you notate these. There's a couple of names that we're going to go through. You don't have to know them. You just have to understand the idea of a sigmatropic rearrangement and how to do it. So first one is a Cope rearrangement. And it's just a straight up 3,3 sigmatropic. It's the first reaction that we looked at. This one is actually showing you a little bit more of an interesting reaction because we've got a methyl group coming off. Looking between the left one and the left reagent and then the right product here, think about which one you think would be more favored. Higher substituted alkenes, that's the only difference between these. Yes, I do have a tertiary carbon, but we're not trying to stabilize a carbocation or anything. So having a di-substituted alkene instead of all mono-substituted alkenes is going to be ideal. That's why that side's favored. Clausen rearrangement is just like the Cope rearrangement, except this one has an oxygen in the middle. Okay, so same type of an idea of these electrons going around the circle, but you have the idea that you can form a double bonded oxygen, which is going to be more stable than a carbon-carbon bond because resonance. Yeah, carbon-oxygen double bond allows for you to have resonance because it's a double bond between 2 different atoms. Next thing we're going to talk about is, we're looking at a Clausen rearrangement that involves, it's a benzene ring, but these are called allylic aryl ethers. Yes, I said that right. Ethers. So the ether body you recognize in the middle. Allylic means that you have the double bond on this chain on the side, and then aryl is because the aromatic benzene ring. So you can do this whole rearrangement that we just saw earlier. I strongly encourage you to take that double bond and rotate it downward so that your double bonds are right next to each other. There is a way to draw them out, and without doing that, it's just a lot harder. So that's what they did from the green to the next one is they just rotated that double bond down, did their cyclic reaction, and then that very next product with the ketone tautomerizes into an alcohol. So tautomerization means that you have the movement of atoms within a molecule rearranging, actually moving, but you don't have anything net coming in or coming out. So that tautomerization is moving the hydrogen from the tertiary carbon up onto the oxygen so that it can reestablish that benzene ring, which is far more stable than a not benzene ring. Now I got a really short video for you. This one I tried to make a little bit slower so we could talk through it. So we can look at the change in the bonds and how they're moving around. So this is showing the arrow pushing. There are 3 arrows around this because it's a 6-member ring, every other bond. So we go from a pi to a sigma, sigma pi, sigma none. Yeah, it doesn't matter. Anyway, so following this around, that's the second arrow. And then there's the third arrow giving you your product, which is inside out ring. And that is all I've got for you guys. So if you have any questions, feel free to email me. I hope this